Okay, I wanted to go through this problem here and just show you how we could do it two different ways. So we could review the nearest neighbor algorithm and the sorted edges algorithm. They're different algorithms that we went through in this graphing theory module, but and sometimes these two different algorithms can give us two different answers. They may sometimes give us the same answer, but it's good to know each one so that when you're given the problem on the test and we ask you to use one or the other, you'll know how to do each one. So I thought I'd show you this one that was in your, it's about a salesman traveling around to these different, or a CEO traveling around to these different cities. And we want to know, it doesn't matter which order he goes in, he just wants to get the cheapest flight path. So this one, the nearest neighbor we'll start with, it's called a heuristic algorithm, which means it's an efficient algorithm that gives approximate solutions. In other words, it is fast to do, but it may or may not produce the optimal path. We call this one a greedy algorithm because at each vertex, the best choice is made without considering future consequences. Sometimes it reminds me of the song from Frozen 2. If you've heard of the song, just do the next right thing. It's something along those lines where you're just looking at the options of the city you're sitting at, and you're not looking ahead too far into the future. You're just greedily taking whatever is the cheapest one for the city you are at. So here's the steps for this nearest neighbor algorithm. We're going to start by selecting a starting point, and we're going to, so I actually just started with Chicago, but I could have started anywhere. Sometimes problems like this will show you what you want to start at. So it'll tell you something along those lines. So if I'm sitting at Chicago, I'm just going to look at the options I have from Chicago. I have a $100 flight, I have 145, I have 165, and I have 75. So since this is a greedy algorithm, I'm just going to choose the flight that's the cheapest, $75. Now this might end up taking me somewhere that has more expensive flights going to it. So sometimes it doesn't look far ahead, and it could end up giving you a solution that's not optimal, but we're going to go with 75. So now I'm sitting at Atlanta. You can kind of see the answer down there. I'm sitting at Atlanta and I'm going to look at the options there. I can go 175, I can go 140, or I can go 85. Again, I choose the greedy option, just whatever's cheapest I'm going to go with. And that's how we do the nearest neighbor algorithm. We just take whatever one is the nearest, and in terms of units, this time it's in terms of money. So now I'm sitting at Dallas and I have some choices. 165 would take me back to Chicago. Now what if that would have been the cheapest? It's not here, but even if it was the cheapest, I wouldn't be able to choose it because I wouldn't want to complete the circuit. I wouldn't want to close this off back to Chicago until I've visited every vertex here. So you have to move to the nearest unvisited vertex. So even if the cheapest one takes you somewhere back to closing a circuit, back to a vertex you've started at, you can't choose the cheapest one at that point because you cannot close a circuit until you've hit everything. So remember that, but in this case it doesn't. I would go with 120. And now I'm sitting at Seattle. I have some choices. I have 70, I have 145, I have 140, but the 140 and the 145 routes would close a circuit. I cannot choose those. Even if they were the cheapest, I could not choose them because they would close the circuit, and I haven't visited LA yet. So it turns out LA was the cheapest here. So we go that route. And then at LA to Chicago. Now, what if that would have been like the priciest one on there? I wouldn't have known that till the very end. Like, what if this was $900? I would have to choose it because that's the only thing I have left. I want to go back to where I started. So you have to move to the nearest unvisited vertex. This is the one I started with. I'm ready to complete the circuit. And that's what I mean by a greedy algorithm. It doesn't really plan for what's up ahead, but luckily this one turned out to be the cheapest one anyway. So we ended up just going on the outside of this shape here, and this was our flight path with our prices. It ended up being $450. So that's some things to remember with the nearest neighbor algorithm. Now let's go to the sorted edges algorithm. It's a different algorithm. We might end up, in this case, with this example, end up with the same answer, but that's not always the case. So remember that you could get different answers depending on the algorithm you use. So the sorted edges algorithm is also heuristic. It's not optimal, so it doesn't guarantee it's the shortest route, but it is a pretty fast way to get a fast route. It again doesn't guarantee the fastest, but it's a quick way, because some algorithms, like a brute force algorithm, could take a long time or lots of computer power to look at every single possibility of combinations of flight paths we could take. So in this algorithm, we find the cheapest unused edge. Note on this algorithm, there is no set starting point. So it's not like I'm starting in Chicago or anything like that. I just look for the cheapest unused edge. I just look for the cheapest edge on here, and I look for the smallest number, and I want to always make sure I'm looking very carefully, because if we just happen to overlook something, it's going to throw everything off. So you want to look very carefully at every single one, look for the smallest one. I can see the smallest one is $70. So I would just highlight that first, and you can even start a new graph over here and say you've hit LA and you've hit Seattle. Like in a test, sometimes it's nice to just create a brand new graphic to the sides, especially if you're using one thing with different algorithms. You might want a different little drawing for each graph so that they're not all right on top of each other. And then we just keep doing step one. We repeat step one, but we don't make a degree 3 vertex. So no vertex can be having 3 lines come from it. And then we don't want to complete a circuit without visiting every vertex. So we just stop once we've completed a circuit. So we just keep choosing edges, and they don't even have to connect. So the next cheapest edge that I can see here is Chicago and Atlanta. And notice they don't even connect, and that's totally fine. Chicago and Atlanta are the next cheapest edge. So I have a 70 edge and I have a 75. And I have not violated any of these rules. I didn't make a degree 3 vertex, and I didn't close a circuit. So I totally have these 2 separate edges to start with. And I just keep looking for the cheapest, and I keep going. So I can choose this one from Atlanta to Dallas. It's the next cheapest. It's 85. I can do that because Atlanta only had degree 1 so far. So now if I connect to it to Dallas, now that's a degree 2. So Atlanta is done. It can't be hit again. Even if there was a cheap line that was going to it, I couldn't do it again because this vertex can only have 2 lines coming from it, degree 2. This is 85. So then I would just keep choosing the cheapest, next cheapest edge would be this 100. And now LA is done and Chicago's done because those both have 2 lines coming from them. They're degree 2. So those are all done. So the only thing I have left to do is 120. Now that may or may not have been the cheapest, next cheapest one, but I couldn't have done any of the other ones because that would make these other ones more than degree 2. So the only possible option I had, even if it wasn't the cheapest, which this one happened to be the next cheapest, just because this was an easy example. But even if it wasn't the next cheapest, I wouldn't be able to choose. I would still have to choose it. I couldn't choose anything else because of these 2. These 3 already had degree 2, and I can't make a degree 3 vertex with this algorithm. So we get the same answer we got in the other one, but we did it a lot different way, right? And so in this case, it ended up with the same answer. So that is 2 ways to do the same problem. We got the same answer in both, but hopefully that helped you review these 2 different algorithms and how they work. Thanks.